Okay, in this video, I'm going to be talking about Bernoulli differential equations. And those are equations that are of the form y prime plus p of x, some function of x, times y is equal to a different function of xq times y to the n. And in this case, n can be any real number, not just an integer, right? Powers of n, we have y to the n squared, n cubed, but it could actually be any real number, like a rational number or an irrational number, in fact. And first off, notice just a couple special cases here. When n equals 0, we end up with y prime plus p of xy is equal to q of x, right? Because y to the 0 is just 1. And so this is just a first order linear differential equation, ODE. And when n equals 1, then we get y prime plus p of x, y is equal to q of x times y. In this one, we can actually subtract q of x and y from both sides and then factor out the y, and we end up with p of x minus q of x y equal to 0. And again, this is a first order linear ODE, and actually the first one here is non-homogeneous unless q of x is 0, but the second one here is actually homogeneous. So, but both in either case, we can use previous methods like integrating factor or maybe separation of variables, all that good stuff to solve these. But if n is not 0 and n is not 1, so n is not equal to 0 or 1, then we can use a special substitution in order to get it into a linear form, right? Because think about this equation, it's first order because the highest derivative is y prime, but it's non-linear because n is not 1. Right? We're raising the function y to some power that's not 1. And so it can't be solved using the regular first order linear methods. However, we can make a substitution. Now, the intuition behind this substitution is not trivial. It doesn't really make sense off the bat, but once you see the results of it, then it really makes sense. So we're going to let a new variable u to be equal to y to the 1 minus n. And when we do that, that means that u prime, the derivative of u with respect to x, is equal to, by the power rule, we bring down the power, 1 minus n, and then subtract the power by 1, so we just get negative n. But also we have to, because y is a function of x, we have to multiply by the chain rule by y prime. And so notice here, now I could use these equations here and transform it and then plug them in to make this an equation of u. But there's another trick that we can do is by dividing this equation by y to the n on both sides. So that's what I'm going to do. I'm going to first y to the negative n, times y prime, plus p of x, and then I'm dividing this term by y to the n, so it becomes y to the 1, right, divided by y to the n, so it becomes y to the 1 minus n. And on the right side of the equation, of course, we just get q of x, y to the n divided by y to the n is 1. And now you can see that right here, this is u. And right here, well, if I use this equation, notice that y to the n times y prime, y to the n times y prime is 1 over 1 minus n times u prime, right? Notice that this expression only contains u as well. And so we can rewrite this. It's going to be 1 over 1 minus n times u prime plus p of x times u is equal to q of x. And you can see this differential equation in terms of u is linear. It's a first order linear differential equation. And so it can be solved using previous methods like integrating factor, variation of the parameter, whatever method you like. And so with whatever n you get, we can solve this equation. And then we'll get a solution in terms of u, right? U is equal to some expression. And then we can back substitute it. Y is equal to 1 minus n is equal to that whatever. And then to get a solution in terms of y. Now maybe it's an implicit solution. Maybe it's explicit. So that's pretty much it. This is the sort of the theory behind Bernoulli equations. Again, they're of the form, they look just like the linear form, except they multiply by y to the n on the other side of the equation, where n can be any real number. We're not including cases where n equals 0 and n equals 1 because those are much simpler. They can just be solved using previous methods. We make a substitution u equals y to the 1 minus n. Take the derivative of that because we're going to need it. And then we do a little trick by dividing both sides of our equation by y to the n to get it into this form. And then the substitutions come very nicely, and we get into an equation just in terms of u, which we can solve, and then substitute back in u equals 1 minus n to find a solution in terms of y.